The topic of this session is Taylor's theorem. Let us see the statement of Taylor's theorem. Let n belongs to n, that is n is natural number, and let I is equal to closed interval ab, and let f is a function from I to r be such that f and its derivative f dash, f double dash up to fn, nth derivative, are continuous on I, and that n plus 1th derivative of f exists on open interval ab. If x naught is any point of I, then for any x in I, there exists a point C between x and x naught such that fx can be written or expanded like this: fx is equal to fx naught plus f dash x naught, x minus x naught, plus f double dash x naught divided by factorial 2 into x minus x naught square, plus and so on, fn x naught divided by factorial n into x minus x naught to the power n, plus fn plus 1 at c divided by n plus 1 factorial into x minus x naught to the power n plus 1. So if this f satisfy all this condition, then fx can be expanded in this form. We use the notation Pn for the nth Taylor polynomial of f, which is given by Pnx is equal to f at x naught plus f dash x naught, x minus x naught, f double dash x naught divided by factorial 2 x minus x naught square, and so on. And lastly, fn x naught divided by factorial n into x minus x naught to the power n. Now this Pn has the property that it and its derivative up to order n agree with the function f and its derivative up to order n at the specified point x naught. The remainder is denoted by Rn. Thus, we may write the conclusion of Taylor's theorem as fx is equal to Pnx plus Rn, where Rn is given by Rnx is equal to n plus 1th derivative of f at c divided by n plus 1 factorial into x minus x naught to the power n plus 1 for some point c between x and x naught. This formula for Rn is referred to as the Lagrange's form or the derivative form of the remainder. Now let us see this example. Expand sin x in ascending powers of x minus pi by 2. Let us see solution. We know that to expand fx in powers of x minus x naught, the formula for expansion is given by fx is equal to fx naught plus x minus x naught f dash x naught divided by factorial 1 plus x minus x naught square f double dash x naught divided by factorial 2 plus x minus x naught cube f triple dash x naught divided by factorial 3 plus x minus x naught to the power 4 f 4 x naught divided by factorial 4. Comparing x minus pi by 2 with x minus x naught, we get x naught is equal to pi by 2. Now fx is equal to sin x. Because we have to evaluate these values fx naught, f dash x naught, f double dash x naught, f triple dash x naught, f4 x naught, and so on, and x naught is pi by 2. So we have fx is equal to sin x implies f pi by 2 is 1, f dash x is equal to cos x, so this implies f dash pi by 2 is 0, f double dash x, the derivative of cos x is minus sin x, so f double dash pi by 2 is minus 1, f triple dash x, the derivative of sin x is simply cos x, so this is minus cos x, so f triple dash pi by 2 is 0. The derivative of cos x is minus sin x, so f4x is sin x, so f4 pi by 2 is 1. So all these values we have found. Now putting these values in this formula, fx is equal to f pi by 2 plus x minus pi by 2 f dash pi by 2 divided by 1, and so on. In this formula, if we put the values, we obtain fx is equal to 1 plus, because this becomes 0, minus 1 x minus pi by 2 whole square plus x minus pi by 2 to the power 4 divided by factorial 4 and so on, which is same as on simplifying 1 minus x minus pi by 2 whole square plus x minus pi by 2 to the power 4 into 1 plus 1 upon factorial 4 and so on. So this is the expansion of sin x in terms of x minus pi by 2. Now let us take this example. Obtain Maclaurin's series expansion for fx is equal to 10x. Let us see the solution. We know Maclaurin's series is a special case of Taylor series by taking x naught is equal to 0, which is given by fx is equal to f at 0 plus x f dash at 0 divided by factorial 1 x square f double dash 0 divided by factorial 2 and so on. We have, because we need these values f0, f dash 0, f double dash 0, f triple dash 0, f fourth at 0. So we need this calculation. For that purpose, let us start with fx is equal to 10x. So value of f0 is equal to 0 because 10 0 is 0. Now find the derivative. F dash x is derivative of 10x is x square x. So f dash 0 is equal to 1. Now finding the second derivative, the derivative of sec square is x is 2 sec x and derivative of sec x is sec x 10x. So this ultimately gives 2 sec square x into 10x. So this implies f double dash 0 is 0 because 10 0 is 0. So this is 0. Now this f double dash x can be written as a 2 sec square x 10x is written as 2 times sec square x is written as 1 plus tan square x into 10x. So this becomes 2 10x plus 10 cube x. So f triple dash x will find the derivative of this term. So f triple dash x is 2, derivative of 10x is sec square x plus derivative of this is 3 tan square x and derivative of 10x is sec square x. So this expression comes. So f triple dash 0, because of 10x this expression becomes 0, sec 0 is 1. So ultimately this is equal to 2. So we have fx at f0 plus x f dash 0 divided by factorial 1 x square f double dash 0 divided by factorial 2 and so on. Putting the values from this in this expression, we get 10x is equal to 0 plus x plus 0 plus x cube 2 by 6, that is 10x is equal to x plus x cube by 3 plus and so on. So we found the Maclaurin series expansion of 10x by this way. Thank you.